In this video, we discuss the idea that differentiability implies continuity, and we look at a few examples. I have a feeling this is going to be a short video. When I say that differentiability implies continuity, I mean that if f is differentiable at a point, that is, if the derivative exists at, let's say, x equals c, then f is continuous at x equals c. And it's relatively easy to see this. So we're saying, okay, f is differentiable at x equals c. That means that f prime of c exists. That means the limit as x approaches c of f of x minus f of c divided by f of c, or divided by x minus c, excuse me, is a finite number. So we compute this and we get a number, a finite number L. Well, with that in mind, if we want to, we can rewrite this expression. Or rather, we can rewrite this expression. The limit as x approaches c of f of x minus f of c. And by multiplying and dividing by x minus c. So this limit is the same as this limit. So we're just taking this and we're multiplying by a well-chosen one. That's x minus c divided by itself. And we can do that because as x approaches c, we're not actually interested in what happens at x equals c. So this is just a number divided by a number, and they're not zero. And then we can rearrange this expression. This is the limit as x approaches c of x minus c times f of x minus f of c, all divided by x minus c. Now this is a limit of a product. And we know that the limit of a product is the product of the limits, provided the limits exist. If we're assuming that this limit exists, then we can conclude that this limit exists. X minus c is of course continuous. So you can just plug in x equals c. And then this limit exists by assumption. And so I get this, which is 0. C minus c is 0. And then this is the definition of the derivative. So we get 0. So I have the limit as x approaches c of f of x minus f of c equals 0, which means that the limit as x approaches c of f of x equals the limit as x approaches c of f of c. But f of c is just a constant. So we just get f of c. So the limit as x approaches c of f of x equals f of c, which is the definition of the of continuity. So we say that that means that's the same as saying that f is continuous at x equals c. Now geometrically, when I think of a function being differentiable, I think of it as having a well-defined tangent line. So when I draw the graph, if the graph is nice and smooth so that I can draw a tangent line anywhere on the curve. So if I zoom in here, or I zoom in here, if I zoom in at any of these values, I've got a tangent line with a finite slope, then the derivative exists. And if the derivative exists, then we know that the function is continuous. Let's say if f is smooth, so if we zoom in at any point, and it looks like it looks linear.
Oh, wait. So
we want the tangent line to exist at every point. We want that slope to be finite. Because we want this limit to be a finite number.
Yeah.
Then f is differentiable. Just intuitively, when I look at this, I say, ah, that's gonna be differentiable everywhere, it's fine.
Fixed, right?
Yeah.
And this says that, or what we've just shown here is that if f is differentiable, it's continuous. So I can not only find the derivative, I also know that all of the points are connected to each other in a way like in a form like this.
Yeah.
But while differentiability implies continuity, continuity does not imply differentiability.
Okay. Yeah, yeah.
And then my brother's dad.
So the implication only goes in one direction.
He's been here the whole time, so, yeah.
Yes.
Or in other words, if f is continuous at x equals c, f prime of c may or may not exist. We can't tell, we can't be sure. Telling us that the function's continuous there does not tell us anything about whether the derivative exists at all. Sorry, I'm having problems with the brightness of the camera at the moment.
But I think I would like, but I was.
I know what it is. There we go.
We're all next to each other.
So here's an example, very simple example, y equals the absolute value of x.
Yeah, we do.
Yeah.
Yeah.
That is definitely continuous.
Yeah, I understand.
Yeah.
Same, not for sure.
Y equals the absolute value of x is x when x is positive. The absolute value of a positive number is just the number. Absolute value of 3 is 3. Absolute value of 5 is 5, and so on. But the absolute value of a negative number is the opposite of that number. So the absolute value of x is negative x when x is negative. And you're saying, I thought it was supposed to be positive. It is, because this is a negative number and we multiply it by a negative to make it positive. So we get y equals x on this side and y equals negative x on this side. It's like you've taken all these points on the line y equals x, and then whenever they were negative, you've just sort of flipped it. You reflected it up so that all the resulting values are positive. And that makes sense to us because the absolute value is always positive except for when it's 0. Now it's easy to see what the derivative of this function is by just looking at these functions. We know what the derivative is. The derivative is the slope. If this is the line y equals x, the slope of that line is just 1. And we know that the slope of a line mx plus b is always equal to the coefficient of x. If you wanted to, you could use the limit definition of the derivative. It's kind of overkill using limit definition, but that's possible. The slope of this line is 1 though. So I think I'll just plot that. And so we get a slope of 1 from 0 to infinity. On this side, y is equal to negative x. And the slope, which is the derivative, is equal to negative 1 on that side. This is y prime equals the derivative with respect to x of the absolute value of x. And that's going to be 1 when x is greater than 0 and negative 1 when x is less than 0. And of course, at x equals 0, that derivative is undefined. So this is an example of a function that is continuous at 0. This derivative does not exist at 0 because we've got a different limit from the left than we do from the right. Another example is y equals x to the 2/3 power. So it's like you take your x to the 1/3, that's our cube root function, and then you square it. So it looks roughly like this. Now, if we want the definition, or if we want the derivative of this function, we can use the limit definition again. And I'm primarily interested in this x equals 0. So I want to take the limit as x approaches 0 of f of x minus f of 0 divided by x minus 0, where this is my f of x. So this is x to the 2/3 minus 0 divided by x to the first. And you can just subtract those exponents. This is x to the 2/3 minus 1, which is x to the negative 1/3. A negative exponent gives us 1 over x to the same exponent but positive. And as x approaches 0, we get different behavior on the left than we do from the right. As we approach x equals 0 from the right, this is a tiny positive number. So 1 divided by a tiny positive number is a large positive number. And I shouldn't really use the equal sign here because the derivative turns out to not exist. So I got positive infinity from the right, but from the left,
We actually started a lot now that you can actually do the technique and they get paid.
taking the cube root of a tiny negative number, the cube root of a negative is negative. This is 1 over a tiny negative number,
Yeah.
which is a large negative number. So we have different limits from the left and the right. So the limit itself does not exist. But I would expect to have a vertical tangent line there. So x equals 0. It's our vertical tangent line. By definition of the vertical tangent, that the limit definition of the derivative gives us plus or minus infinity. But we can see what happens on this side. The limit or the slopes are getting more and more positive. On this side, the slopes are getting increasingly negative. And that's why we get different limits from the left and the right. So what have we shown? I've got a continuous function here, and the derivative doesn't exist there. And it happens to correspond geometrically to this vertical tangent. Because these limits are infinite, plus and minus infinity, we say y equals x to the 2/3 is not differentiable at x equals 0. That it does have a vertical tangent line.
Go help, wing that, all my mates say that. You have pen and paper. Put it in the blog.
Okay. So just intuitively, if I see a cusp or a sharp corner on my graph, that's when I'm thinking to myself, the derivative doesn't exist there. So I have a derivative that doesn't exist here and a derivative that doesn't exist here, because the limit from the left and limit from the right are not the same. Or alternatively, these limits are not the same, but in particular, they're infinite. These limits technically don't exist, but they don't exist in a very particular way, so we use this notation. So continuity does not imply differentiability. You can have continuous functions where the derivative doesn't exist. But this derivation shows us that if the derivative does exist, we're guaranteed that that function is continuous at x equals c. So differentiability, which means that the graph is nice and smooth with tangent lines that all have finite slope. That means if we can see that on the graph, then we know the function is differentiable and it's also continuous. So we have differentiability and continuity does not imply differentiability. And of course, if a function is discontinuous at a point, the derivative does not exist as well. All right, so that's it for this video. The next video, we'll look at some differentiation rules, derivatives of some basic functions. We will do a couple of derivations algebraically as we have in the past using our limit definitions. But primarily we'll look at graphs and just come up with some intuitive reasons why these differentiation rules should be true. And then we'll get away from that limit definition or those two limit definitions and then focus on learning and applying the differentiation rules to compute derivatives.